So when we perform regression, it's important to realize that we have 4 different types of equations that we can use to calculate and determine that regression line, estimate that unknown y variable of interest based off of at least one or more X predictor variables. And so these are broken down into what I'll call the form equations, and then we'll get into the prediction equations, which is really what this lecture is all about. So the first of the 4 equations is called the sample form. And the sample form, you can see, is calculated as y, the value I'm trying to determine, the actual y, not predicted, and that's going to be equal to a plus bx plus e. The a is going to represent the y-intercept, the b is going to represent the slope, the x is going to represent the x predictor that I'm using in my equation, and the e is going to account for the variance or the standard deviation or the error that surrounds that particular data point. And so if we know from our calculation of deviance how far that particular score is from the mean, and we know the y-intercept, the value of y when x equals 0, we're going to be able to precisely determine this person's actual y value because we have the error components, we have the person's slope, we have the person's x value, and so we can determine definitively what this person's y value is that was measured as part of the research experiment. The problem, though, is remember, in statistics, we're dealing with sample statistics that we're trying to project to population parameters. And so if we want to project it accurately to the population and not worry about whether our sample is different from other samples in the population, we need to use what's called the standard score form or standardize the sample form. And so as you can see from this equation, y will be determined by having it equal to alpha plus beta x plus epsilon. And so in this particular case, you're just standardizing the y-intercept, you're standardizing the slope, and you're standardizing the error term in this particular case. But this would be more reflective of the true population. You'd be able to use this type of equation with other samples because it's standardized to the population, whereas in the sample form, the equation is confined to just the sample that you're calculating. The other 2 types of forms that I think are really important to understand, really in the context of how we move forward in this lecture series, is what's known as the raw score prediction formula and the standardized prediction formula. And so in the raw score prediction formula, you can see that the formula is calculated as y predicted, the prime means predicted, and that's going to be equal to a, which represents the y-intercept, and b, which represents the slope, and x represents the person's x predictor value measured as part of the research experiment. And so this formulation, unfortunately, is also tied to the sample in which it was generated, right? Means and standard deviations of this group of people with which we collected this data. And so any type of regression that I generate from these people is only confined and works with the people who I collected it on. If I want to standardize it to the population, meaning I want to use this equation with other samples that reflect the population in which I'm studying, then I need to use what's called the standardized prediction formula, where I'm going to take the z, or standardized version of the y predicted, and I'm going to, again, replace the b with beta, which is the standardized version of the slope, and the z-score for the x statistic. Notice here, however, that this particular form does not have a y-intercept. And the reason for that is because, remember, in a perfect z distribution or a t distribution, the mean, the median, and the mode is always going to be 0. And so we don't have a y-intercept when we're talking about a standardized form. And so we only need the beta, the z-score, and the x value in order to calculate that. So these are some of the formulas that we can use when we're trying to determine and generate a regression line. The last thing